Alright, so impulse. Impulse is the force that two objects apply on each other multiplied by the amount of time that these objects are in contact or applying the force on each other. So that would just be force multiplied by T is equal to J, the variable of impulse. Impulse is kind of hard to visualize, but if you take a bouncy ball that's kind of squishy and you drop it from a certain height, doesn't matter, to the floor, once that ball hits the floor, it would flex just a little bit, probably noticeably with like high-speed camera or something like that. But so this would be its original height, and this is what the height would look like there. So it would be smushed, and once this is squished, it kind of acts like a spring. And when the spring decompresses, it would apply a force on the center mass of this ball to propel it back up to hopefully close to its height, except it would never do it because when this flexes it loses some energy. Anyways, so the time at which this ball is compressed would be the impulse multiplied by the force that this ball is resisting the compression would be. So this graph of force times time would be force in newtons, time in seconds. It would look kind of something like this. This being when the ball is fully compressed, this being when it's just touching the ground, falling, kind of slowing it down, and this around here would be right when it's about to shoot up to go back into the air. And if you notice that this is time and this is force, if we multiply these, we could get the impulse. So the area under this graph right here would be the impulse. And just as in this graph, if the force isn't constant, you could integrate the graph of force times time, so it would be the integral of f dt, and that would also give you J, the impulse. Alright, so now on to momentum. Momentum is the relationship between an object's mass and its velocity. So it would be mass multiplied by velocity would give you P, the variable for momentum. The law of conservation of momentum states that if no external force acts on a system, the momentum of that system will stay constant, whether it be zero or something else. So if we look at the example of a gun, fairly crudely drawn gun, shooting a bullet in this direction. So let's say the bullet is going in the positive direction, so positive, negative. So the bullet with a velocity, originally the bullet would be in the gun and neither of them would be moving, so the momentum would be zero. And once the bullet is shot with its small mass, m lowercase, and the mass of the gun, m uppercase, the bullet would be going with the velocity positive, a high velocity positive this direction, and the gun with the recoil would be going in a slower velocity in this direction. So the positive momentum of the bullet and its high velocity have to be equal to the negative momentum of the gun and its bigger mass but smaller velocity, which would equal to zero, just as they were when the bullet has not been fired yet. So that's the just momentum. You could deal with it with many different scenarios. This is kind of an explosion. You deal with two objects colliding, two pieces of clay, a clay of big M and a clay of small m colliding. This one's at rest, so it would be mv, and this is zero, so this initial momentum is nothing, would be equal to both of their masses together and their final velocity, so m plus M1 V final. This leads us into our next thing, collisions. So there are 3 different types of collisions. There are elastic, inelastic, and perfectly inelastic. So elastic would a scenario in which there would be an elastic collision, or when there are 2 rigid objects, something like 2 pool balls that would collide with each other. So 2 pool balls of mass M1 and M2. For the sake of argument, just say they are 2 different masses, and this pool ball is shot at a velocity with velocity at the second pool ball. This means that the initial momentum of this pool ball would be M1 V naught and plus M2 V naught, which is 0, so this just cancels, is equal to M1 V final plus M2 V final. These 2 V finals are going to be different if they are 2 different masses. However, if these 2 are the same masses, then this is just a property of when they're the same. The velocity at which this one's traveling, this ball would stop, and this pool ball will continue at that same velocity. So all the momentum would be transferred into this ball. So if it was M colliding with M, same mass, this one would come, stop, and then the other one would shoot off with the same velocity as these right here. Another property of elastic collisions is that energy is conserved. Energy is only conserved in these and not in either of these. So we could do it with this one here, I guess. So the energy of pool ball number 1 would be 1/2 mv squared, and the kinetic energy of this would just be 0 because it's not moving. And so the kinetic energy initial would be equal to the kinetic energy final, and the kinetic energy final would just be 1/2 m, this pool ball, v squared. So you can see different pool balls, and since they're the same masses, they have to have the same velocities. Alright, so I'm going to skip an elastic for now, but then I'm going to say something about it later. But so an example of a perfectly inelastic collision would be something that I showed off in momentum. It would be if 2 clay cubes, I guess, of big M and small m collide at each other. Let's say they both have velocity. Actually, just say that this one has velocity just for the simplicity of it. So in this, only momentum is conserved. We can't say that energy is conserved, and I'll explain that later. But the initial momentum of this would be big M v, and the initial momentum of this would just be 0, so I'm not going to write it right now. But the initial momentum is equal to the final momentum, and the final momentum would be these 2 masses added together because they collide and then they get stuck, which is the meaning of perfectly inelastic, where it doesn't rebound at all. So it would be M, big M plus small m, V final. V final being smaller than V initial because it's moving with more mass. However, in this situation, energy is not conserved, because when we were looking at, just like how we were looking at impulse, there is kind of flexing going on, inevitably there has to be. And when an object moves or is misshaped, the force of friction between them and stuff like that takes the energy and turns it into heat, which means that there is going to be less energy in this in the final after the collision than before the collision. And so for inelastic, which is kind of in between perfectly inelastic and elastic, momentum is conserved, but energy is not, and it falls in. This is where most of the collisions fall in, because most collisions are never going to be perfectly elastic or perfectly inelastic. So it's basically the same as an elastic, except the objects will lose energy, but they won't exactly stick together. So it would be more like two exercise balls that collide with each other. I'll write it down here. So an exercise ball of mass 1 and an exercise ball of mass 2 collide, and this one's going in a velocity smaller than this one. So when they collide, these two flex a little bit, but they don't get stuck to each other, so that the momentum initial or these two momentums added together. So it would be, this is positive direction, this is negative, so it would be negative m2 v2 would be equal to the final momentum, which, depending on the situation, would either be both balls moving in this direction, this ball stopping, and this ball continuing, or actually I think those are the only two situations. So let's say they were both continue moving in this direction. So m1 v final 1 plus m2 v final 2, because they're both moving in the positive direction. However, energy is not conserved in this, because whenever there is flex, like I said earlier, the flexing of an object creates heat, and energy is lost in that heat. So you can't say that energy is conserved. The answer just won't come out right. It just won't work.
And also remember, for momentum, for the conservation of momentum, that the momentum is conserved within the system. So the two objects, each example shows two objects. So for each system with the two objects, the momentum is always conserved. If there's a force outside of the system, then momentum is not conserved in the system.